So what we're going to look at in this video is we're going to expand finding solutions of polynomials to start to include complex solutions. Now, up to this point, whenever we've worked with polynomials, we've found real solutions, but any time we've looked to solve a quadratic, for example, and we've done b squared minus 4ac, and we've got a negative number, we've always said no real solutions exist. Well, that's because the solutions at that stage are complex. So what we're going to start to do is expand those solutions and look at finding the solutions in a complex nature themselves. Now this all extends back to the work of Carl Friedrich Gauss in 1799. What he did was he proved that every polynomial equation with complex coefficients, so any complex equation written in the form f of z equals 0, where z belongs to that complex set of numbers, has at least one root in the set of complex numbers. So it's got at least one complex root. And he called this the fundamental theorem of calculus. Now our main focus will be looking at real coefficients. Now this theorem will still apply purely because we're able to cheekily write every real number in a complex format. The only difference is the coefficient of the imaginary part is 0. So technically every number we work with is a complex number, but no coefficient in front of the imaginary part. Now there's three key theorems associated with this that we need to be able to remember, and we need to be able to think about how we can prove them and work effectively with them. So the first one is that if the root of a polynomial with real coefficients is non-real, so of the format r cos theta plus I sin theta, where sin theta doesn't equal 0, so it has to be complex, then its conjugate, r cos theta minus I sin theta, is also a root. Now this one, we can prove that by imagining that if we've got f of z equal to 0, so our polynomial we want to solve, and we write f of z in the format an zn plus an minus 1 zn minus 1, and so on and so forth, all the way down to our final term, which is quite simply a constant a naught. What we're then able to do is use the fact that we think and we know that z equals r cos theta plus I sin theta is a root and substitute that in. So if we were to then substitute that in, we'd get an r to the n. Now what I'm going to do is I'm going to use De Moivre's theorem to simplify this, because I'll have cos theta plus I sin theta to the power of n. That would be able to be written as cos n theta plus I sin n theta. I'd then have plus an minus 1, r to the n minus 1, and again I can use De Moivre's theorem to write this out. The only difference being, instead of cos n theta and sin n theta, it would be cos n minus 1 theta sin n minus 1 theta. So the coefficient of theta goes down by 1 every single time. So it would then be cos of n minus 1 theta plus I sin of n minus 1 theta. And again, we'd continue that all the way down to a final term, which is a constant plus a naught. Now for that root to exist, we also know that that has to equal 0. So let's imagine I then take that, I multiply out the brackets, and I split it into the real parts and the imaginary parts. So if I split it into the real parts, what I'll end up getting is an r to the n cos n theta plus an minus 1 r to the n minus 1 cos of n minus 1 theta. And again, that will continue all the way down, and it'll include my final constant there, the a naught, because that is just written in terms of a real number, if you like. We know that that is going to equal 0. If the whole thing equals 0, my real part has to equal 0, and similarly, my imaginary parts has to equal 0. So what I'd have for the imaginary part is I'd have an r to the n. This time though, it would be sin n theta plus an minus 1 r to the n minus 1 sin n minus 1 theta and then that would continue all the way down. It would stop though at a1 r1 sine theta. And we know that that also would equal 0. So the imaginary part and the real part that take that format have to equal 0. So let's imagine I then look at the conjugate, z bar, which we know would be given by r bracket cos theta minus I sine theta. So if I know it's that, and I do f of z bar, I can do it in a similar fashion to what I've done here. So f of z takes this format, and I substitute in z bar. What I'll end up getting is an r to the n. Take the similar format using de Moivre's theorem, I'd get cos of n theta, but this time it would be minus I sine of n theta. That would be the only difference in the terms as we would go down. I'd then have plus an minus 1 r to the n minus 1 cos of n minus 1 theta, take away I sine of n minus 1 theta, and again that would continue on and on all the way down to plus a naught. What I can then do is similar to what I did before, split my real parts and my imaginary parts. So multiply out all the brackets and split real and imaginary. So what I'd end up getting is I'd write that as an rn cos of n theta plus an minus 1 r of n minus 1 cos of n minus 1 theta. That would then continue on, again all the way down to plus a naught. I'd then have take away I, because I'm just going to take the subtract out as a factor for this one as well. I'd then have an rn sine n theta plus an minus 1 r to the n minus 1 sine of n minus 1 theta. And that would then continue all the way down until I end up getting plus a1 r1 sine theta. So there you go, I've split it into real and imaginary. Look at it and compare it with this part here though. This first part, the real, equal to that equals 0. This part here, the imaginary, is equal to the imaginary part here. That's also equal to 0. So f of z bar equals 0. So what we can then say is therefore z bar is a factor. Z bar has to equal a factor. So there you go, we've shown that one. Second one, a polynomial of degree n will have n complex roots. So let's imagine we've got a polynomial, f of z, it's got a degree n, and f of z equals 0. Well, we know for that kn is a solution. Yeah? So kn is a solution using the fundamental theorem of calculus. So what that then means is that z minus kn is a factor. So if z minus kn is a factor, that means I can write f of z in the format of z minus kn times some other polynomial, let's call it g of z, where g of z is 1 power less than f of z. So if f of z's highest power was a cube, g of z's highest power would be a squared. Then I can look at g of z and say, fine, so g of z has to have a solution kn minus 1. So what that means is for g of z, z minus k of n minus 1 is also a factor. So what that means is I can then rewrite it again as z minus k of n bracket z minus k n minus 1 times, again, let's call it another polynomial, h of z. Again, highest power of h of z is now 1 less than g of z. I can continue this on and on and on, and what I'm then eventually able to do is rewrite f of z in the format z minus kn, z minus k n minus 1, continue on and on and on until I get z minus k1. So I've got n complex roots for that polynomial. Last theorem is that a polynomial, degree n, with real coefficients can be reduced to the product of real linear factors and real irreducible quadratic factors. So let's imagine that k is a real root. So if k is a real root for this one, what we then get is we get a factor z minus k for a polynomial. Now remember, z is complex. Because z minus k is a root and it's a real factor, what that then means as well is z minus k bar, so the conjugate, is also a solution. Now what we then do is if we multiply these out, so if we do z minus k times z minus k bar, what that then gives me is an irreducible quadratic in real numbers. Irreducible in real numbers because I'm going to have a complex part of it. There's no way we can have it without that. So these three theorems are fundamental to the work we're going to do. I'm going to show you one quick example of working with them just to demonstrate them. So let's imagine I've got a polynomial f of z equals z to the 4 minus 6z cubed plus 18z squared minus 30z plus 25. I'm telling you it's got a root z equals 1 plus 2i. I want to find the other roots. So it's a power of 4. It's going to have 4 roots. First root z1 is 1 plus 2i. So based on the theorems that we've talked about before, I've also got a root 1 minus 2i. So z1 is 1 plus 2i, z2 is 1 minus 2i. What I can then do is if I multiply them out, I do 1 plus 2i times and 1 minus 2i. And what I'll do is I'll do z, take away the 1 plus 2i. And I'll multiply that by z, take away the 1 minus 2i. So z take away each of the two roots. If I multiply those out, gather all the like terms together and see what I get, what I'll end up with is I'll end up with z squared minus 2z plus 5. So that's what this part here is. So for f of z, what that means is I'm going to have f of z is going to equal z squared minus 2z plus 5 from these two first roots times some other polynomial, but in this case we know it's a quadratic, with the highest power of 2, which will give me the other two roots of the polynomial, the other two complex roots. So what we have to do is algebraic long division in order to get that. So what we have to do is z to the power of 4, take away 6z cubed plus 18z squared minus 30z plus 25, take the original equation, and what we'll end up doing is we'll divide it by the z squared minus 2z plus 5 using an algebraic long division. Now I'm going to leave you to work through the steps of that, and what I'm going to tell you is that the solution we get to that is z squared minus 4z plus 5 if we do it. And again, the check to this is right at the end there should be a remainder of 0. So the complementary real factor is given by this, and in order to solve this we use our quadratic formula. So for this we use z equals negative b plus or minus square root of b squared minus 4ac. So z is going to equal 4 plus or minus the square root of b squared, so 4 squared, which is 16. Take away 4ac, take away 4 times 1 times 5. If we take away 20, it's going to be all over 2a, which is going to be divided by 2. If I then split that, what I end up getting is 2 plus or minus root 4i over 2. Root 4 is 2, so I end up getting 2 plus or minus I. So what that means is I've then got 4 roots of the equation. I've got the first two I've got there, 1 plus 2i. I've got 1 minus 2i. I've got 2 plus I. And I've got 2 minus I. So working it through, following the information and the 3 theorems I've talked about, we're able to get all the roots of that, so all the complex roots of the polynomial. It is a fairly straightforward set of steps, just remember the information here and the key properties and theorems we've got.